Bismillah ar-Rahman ar-Rahim. Welcome to the podcast. My aim here is to share information and to give people more career insights, especially in the energy industry. Today I have a guest who's a very dear friend of mine. I've known him for maybe 16, 17 years, something like that. Majd Badawi, would you like to introduce yourself? And of course, thank you very much for taking the time and being here with us to share your expertise and knowledge and educating me and some of the listeners more on hydrogen and the future of hydrogen and where we are and the opportunities for electrical engineers. So over to you, Majd, if you would like to introduce yourself and give us a bit more about your professional background and experience.
Thank you, Muhammad. It's really nice talking to you after a fairly long time. And I would say it's time to pay back or pay it forward a little bit, because I would say you were one of the first one who educated me and introduced me into the power systems and the basic principles of the power systems and how we automate it and how we control it and how we protect it as well. So I think after about 15 years now, it's really good time to catch up. We've been talking together multiple occasions. That doesn't mean we didn't interact. So a quick introduction about myself. My name is Majd, and basically I've been for the last 15 years in the energy sector, working from utilities in the transmission and distribution segments to the energy segment as well, to the oil and gas. I worked a bit in the oil and gas field, in the upstream and in the downstream with the petrochemicals industry. Then in the last 2 years, I decided to move to a cleaner side of the energy sector, working as a business developer for green hydrogen.
Very good.
That's on the business side. On the personal side, even though I wouldn't say I'm a big fan, but I like learning languages. My native language is Arabic, and hopefully I am fluent in English. Let us see that.
Yeah, very
But
fluent.
I also learned the conversational French and now working on my German language skills.
Amazing.
I'm a father of two, so I'm not left with so much time these days to practice hobbies. But when I can, I do play some sport. I like playing paddle. It's fun. And I mean, the rest of the time, I just read or watch Netflix.
Amazing.
Yeah.
So where are you based now, Majd?
I'm based now in Switzerland, in a small town, I would say, called Baden. And Baden is a very interesting city because this is where the famous power systems company, ABB, or the Brown Bovary of ABB, has started about 100 years ago. So if you walk in the city, you find the founder's house. The founder's basically a palace, not even a house. The very first factory where they started the transformers. This is where the first train connection started in Switzerland between Baden and Zurich in order to export Brown Bovary transformers and production systems. They're the one who brought the electricity to Switzerland. So I'm very proud to be based in and nearby, basically, this town.
Hydrogen. As you know, I've been in substations and power grids in different sectors, but one of the sectors that I know very little about is hydrogen, and this is why it's a great opportunity for me as well to pick your brains and understand more what's happening in that field and what kind of opportunities are presenting themselves to engineers, specifically electrical engineers, but to the wider engineering community as a whole. I'd like to learn more about hydrogen from you. So what's the story of hydrogen and why is it considered cleaner or a clean source of energy?
All right. So let us start with the hydrogen itself. Hydrogen is a molecule in the table of chemistry. Okay, it is the first molecule
Periodic table.
on the periodic table. It's the first molecule on the top left, basically. And it's been around since the beginning of history. And there is also a slogan or a motto that says hydrogen is the most abundant molecule in the universe. This is because mainly theory says that the stars, the sun is mainly made of hydrogen. That is the fuel of these stars and the fuel of the universe. So it is an element that has not been used and utilized, and there is huge quantities existing naturally, however, not around us. On Earth, if you would like to get hydrogen, there is the traditional way of getting it, which is burning methane. Breaking methane, which is CH4 as a formula, taking the hydrogen out of it and producing CO2 as an emission. So this has been historically the major way of producing hydrogen. And this you cannot consider as clean, releasing CO2 into the atmosphere. Now, what is changing is basically that we are at a time where renewable energy is becoming more available and affordable. And with the presence of renewable energy, we can provide energy and connect energy into a chemical process called electrolysis. And this chemical process, once you put water inside the electrolyte, you split the hydrogen into oxygen and hydrogen, releasing the hydrogen to the atmosphere and storing hydrogen. Sometimes they store oxygen if it is required. So also this process has been there for a long time, however, not at scale. Scale today is what can bring a difference into this market. And for the first time in history, we're able to produce hydrogen at huge quantities from a renewable source. So hydrogen itself, it's existing in the universe, very small quantities in the nature here on Earth, but the main breakthrough today is to make it renewable, is to produce it from water and renewable energy.
Yeah. And, I really enjoyed this because, growing up, chemistry was always my favorite subject. People think that because I'm an engineer, my favorite subject was math and physics, and they were, but chemistry was my number one subject. I really loved it. And so we hear about green, gray, and blue. So some colors in hydrogen. What does that mean?
Yeah. So, by the way, they're all hydrogen.
Okay.
Green, blue, gray, they're all hydrogen. They don't change. The hydrogen molecule stays the same.
Mm-hmm.
However, what changes is the way we are producing hydrogen.
Mm-hmm.
Let us start with the first one, which is the gray. In the gray hydrogen, this is the most common type of producing hydrogen today. Using natural gas and without any carbon capturing. This is resulting significant carbon emissions. As I told you, for gray, we break methane. We break natural gas or with coal. Now, if you apply a carbon capture technology on top of the gray hydrogen production, which is adding sort of, consider it as a filter layer that captures the carbon, store it, and sometimes utilize it, sometimes just store it underground, and then release what is left into the air. Mm-hmm. This is what we call blue hydrogen. Now, this process captures up to 89% of the CO2 emissions that could result from the gray hydrogen. Mm-hmm. So itself, it's a huge advancement in reducing the carbon emissions for an existing plant. Mm-hmm. Now, leave these two aside and let us talk about green hydrogen. Green hydrogen is a completely different process that does not rely on fossil fuel and uses the combination of renewable energy and water, which are both inserted into an electrolyzer because it's an electrolyte process to split the water into hydrogen and oxygen. And if the energy is coming from a renewable source, which is solar, wind, hydropower, and in some definitions, nuclear power as well, then it is considered as green hydrogen.
Okay.
This theoretically eliminates all emissions that is required to produce hydrogen. Of course, if you want to trace back the emissions through the supply chain, this is another important topic that companies start to recognize and start to do so. But theoretically, we're reaching a completely renewable way of producing green hydrogen. There are other colors of hydrogen, like pink, sometimes for hydrogen produced using nuclear power, or turquoise using pyrolysis process. So there are different colors. However, these three are the most common ones, and they cover 99.9% of the hydrogen that is produced today.
And what are the main applications where hydrogen can be deployed and utilized? So where do we see that making a difference and making it very appealing as an alternative energy source and maybe energy storage means as well?
A very good question, because the first thing that comes to mind when we start talking about hydrogen in general is that, okay, we will use hydrogen to generate power again. And this is correct. So there are many applications where hydrogen can be used in fuel cells in order to power vehicles, for example. As we know, that Toyota produces vehicles that uses the fuel cell for generating electricity to the car. So definitely transportation segment is one of the applications where we can use green hydrogen. And there are ideas for using green hydrogen in aviation and sometimes in ships as well, in a mix with the gas that fuels the ship in order to reduce the consumption of the fossil fuel gases.
Yeah.
Then there are multiple other different applications, like power generation using hydrogen as a fuel, industrial feedstock, which is a very important application, and this is where mainly we have the most utilization of green hydrogen.
With the transportation, we're talking about hydrogen being a competitor to batteries. Then is that how we look at it?
So we're talking about here the fuel cell is the competitor to the battery.
Yeah. Okay.
Hydrogen is the fuel for the fuel cell.
Yeah.
Which is a chemical process, and the output of this process is water. So they are a competitor to electric vehicles as well. Now there are companies that are trying to create combustion engines using that burns hydrogen instead of fuel. There has been some announcement. We haven't seen anything in reality yet that is efficient as well. Now, before going to the industry, let us stay a little bit in the electricity and the energy segment. So hydrogen can be used as in power generation, can be used as an energy storage, because if you produce hydrogen and you are capable to store it for a long duration, this is not achievable, and as much capacity as you want. This is not achievable just with BESS, with the energy storage systems. So they can act as a long-term storage for the renewable energy whenever you have excess.
Mm-hmm.
And one of the applications is heating and district heating, because through the production of green hydrogen, you emit a lot of heat. And once the plant has a scale, then this heat can be used and recirculated into the district heating application, which is apparently common in Finland. I've seen a couple of projects in Finland where there are real applications for reusing the heat emitted by the green hydrogen production and injecting it into the district heating application. Now, the third one is hydrogen as a feedstock for the industry. And there, this is, I would say, the widest use for green hydrogen. It is used in multiple industrial processes as a feedstock, like in ammonia production, which is an important input for fertilizers. So we have green fertilizers. In the steel production process, especially in the iron reduction, which means when we bring raw iron and we heat it up to convert it into pure steel. And then also in the steel production for the steel rolling, it's used to heat up the steel in order to enable the rolling and the spreading of the steel sheet. Also in the methanol production, in the desulfurization process in the refineries, and many other applications. So hydrogen is extremely important, and this is where today the majority of the consumption of hydrogen as an industrial feedstock.
Okay. So you think that, or is the situation at the moment is that it's not widely deployed or not easily, let's say, going to be deployed in the next 5 to 10 years in transportation?
If we talk about green hydrogen, I would say this would not be the most wise utilization of green hydrogen.
And why is that?
Challenging, there are solutions, and we are finding solutions for how to use hydrogen in trucks, for example, and how to distribute it to refueling station. However, it is not the most wise application for green hydrogen specifically. It's because the efficiency of the process itself. The green hydrogen is already more expensive to produce in comparison, we can talk about that later, in comparison to other traditional ways of hydrogen production. This is number one. Number two, in the process of converting renewable energy into green hydrogen, you lose about 30% of the power of the value of the power that has been produced. So the process efficiency in best case scenario is about 70%. Now, to convert hydrogen through the fuel cell again into electricity to be used in transportation, the efficiency of this process is again another 60%. So basically, you're losing about 70% of the power that you have produced in the efficiency losses for the hydrogen production and hydrogen utilization.
What would be the optimum use of hydrogen in electricity applications or in the energy applications?
Let me break it into two questions. The first one, what is the ultimate and the most beneficial use of hydrogen? Today, I would say, and let us talk about green hydrogen specifically. Green hydrogen is a great replacement for the gray and the blue hydrogen. And the ultimate use of it today is the using it directly as a feedstock into industry, because there you don't convert it into any other elements. It just becomes directly a participating part in the production process of XYZ. They call it power to X, which means converting power into multiple applications. Okay, so if you're not able to electrify and you rely on hydrogen in your process, the only way to decarbonize your process is to use green hydrogen.
How can hydrogen be integrated in energy grids, specifically electrification? electrical power.
Integrating hydrogen into the energy system and the ecosystem of mainly, let's talk about renewable energy. Now, number one, we need renewable energy to produce green hydrogen. And green hydrogen can act as a long-term storage for renewable energy whenever there is excess in the generation. This is one of the applications of green hydrogen, even though that's not the major one. As I said, there are losses in the conversion process that happens once you convert. So once you store green hydrogen, you lose some of the energy that you have produced, and when you convert it back again. However, today, the scaling up of electrolyzers allows us for the first time to build green hydrogen plant at scale. In the last, let's say, in the years between 2000 and 2020, the scale of the plant of the green hydrogen was between a couple of hundreds of kilowatts and maximum 5 megawatts. Recently, in the last 5 years, we started noticing the scaling up of green hydrogen plants. So we started seeing plants of the scale of 10 to 20 megawatts. Now, in the last 2 years, we started seeing plants in the scale of 100 megawatt and above. There is even the most ambitious project in Saudi Arabia, in nearby Neom city, where they are building a 2 gigawatt scale for the first time in the world.
Wow.
Now, imagine a scale of 2 gigawatt plant only coming from renewable energy. This means that you need a stable supply of 2 gigawatts of electricity from renewable sources.
Yeah.
And in order to do so, they have to build double of this capacity of renewable energy to avoid any dips in the renewable generation. So they are building approximately, and I'm not giving exact figures here, but they are building approximately 2 gigawatt of wind energy, 2 gigawatt of solar energy, and 500 megawatt of energy storage, which means batteries, in order to compensate for sudden dips in the power generation. And on top of that, they connected this energy network into a 400 kV high voltage substation network with a connection toward the grid in order to bring the startup power into the plant. So when you're starting from zero, you need some startup power, and to regulate the frequency of the entire grid backbone, which is bringing inertia into the grid.
Yes.
So this itself a very interesting topic, because in order to produce, as we mentioned, in order to produce green hydrogen, we rely on electrolyzers. And electrolyzers are a DC component. They don't use AC current. They are like a battery with an anode and a cathode and a liquid in between. I think we will come to this later on, but they are a DC component. And this DC component becomes at the scale of 5 megawatt in one block. However, what lacks the DC system is the frequency that governs the grid and the inertia of the grid that allows, in case of discrepancies, to maintain the frequency of the backbone system. So in some cases, there are multiple applications where, sorry, let me take it a step back. We need to convert in order to connect to these electrolyzers. We need to convert the AC power on the generation side into DC using power electronic rectifiers. And at the same time, we need to maintain the inertia of the system by bringing some frequency regulating either from the grid or via a grid forming inverters that maintains certain frequency and allows the grid to stabilize. So there is a very strong relation between the green hydrogen and the electricity. And that's why all of a sudden, green hydrogen become a very interesting topic for energy producers and for transmission system operators. Because one, this brings a large-scale load into the grid, and this large-scale load is DC, which is fundamentally different at scale from connecting AC load, which the industry is used to.
Yeah.
So green hydrogen is an extremely interesting industry for electrical engineers due to the electrification of the production process. Everything is electrified from generation, transmission, the power conversion, up to the electrolyzer itself. Then the output of the electrolyzer become a process thing where you get hydrogen and oxygen, where you need to compress it and store it safely and then distribute it or connect it into the process or the backbone network. So I hope this clarifies a bit the relation between green hydrogen and electricity. Yes, hydrogen is an important energy source that can be used again to be converted to energy. However, the reason why green hydrogen is interesting for electrical engineers is because its process is electrified. And it's not just a petrochemical process, it's not a gas production, it's not a cement production process or steel. We're producing a component where its process is electrified down to what we call the stack and the electrolyzer.
So that's interesting. So you see that the demand for electrical engineers is going to rise in that area over the next 5 to 10 years, you would say?
I would say it is developers and green hydrogen producers, they already recognize that. And they already recognize on the importance of studying and analyzing the electrical component of the process at very early stages of the project, starting from what we call FID. Let me brief you about how a green hydrogen project starts.
Sure.
Basically, an investor starts considering investing in building a green hydrogen plant. This investor can be a gas producer, can be a utility, and can be a private investor that invests in renewable sources of energy or in renewable hydrogen. In order to do so, they do a feasibility study in order to decide whether the hydrogen molecule he will be producing is commercially profitable.
Yeah.
And in order to do so, he needs to analyze the main cost of the main cost drivers for the hydrogen molecule to be produced. And 70% of the cost of green hydrogen production comes from electricity cost. So this is on the operational side and 25% on the capital side. Okay? So in order to understand whether the project will be viable and profitable or not, he needs to analyze how much the electricity backbone system will cost him, and what will be the price of energy he will be paying per megawatt to produce his green hydrogen, in order to get to the calculation and to understand whether the project is viable or not.
And I heard it's costly now right? So it is still considered very, very costly to produce hydrogen with green hydrogen, of course. So using that electrolysis process. Is that right?
So this is 100% right. Today, the very or the most optimistic estimates states that the green hydrogen is 6 to 7 times more expensive than the gray hydrogen. So the gray hydrogen, they call it, let's say, euro per kilo. The gray hydrogen cost 1.5 euro per kilogram of hydrogen. The green hydrogen costs between 7.5 and 12 euro per kilo.
Compared to then, I would say, I don't know how to compare it to electrical terms. So again, this is me trying to educate myself, but how do you compare? You can compare the green hydrogen to gray and blue hydrogen, but how do you compare it to let's say if I want to find out, I'm an investor and I want to find out whether it's more cost effective and more, profitable for me to build an energy storage, battery energy storage system, or shall I go with hydrogen? So how do I compare that if there is such a comparison?
Right. I would say you're not comparing apples to apples.
I felt so.
The application is completely different, and the comparison is completely different. So the batteries, how much can you build? 100 megawatt?
No, you can go up to, you can go up to
800
1
megawatt, couple of gigawatts. Yes, but that's it.
Yeah.
And the batteries are much have a fast response and can be connected into utilities at a utility scale, while this is not the case for fuel cells yet. So the battery is a very mature product when it comes to injecting electricity via inverters into the grid. While the hydrogen, the application is it is commercially feasible. It's a heavy capex investment, and it is commercially feasible only when you want unlimited storage for excess of renewable energy. So we are generating a lot of renewable energy in the North Sea, for example, and at night this energy is not consumed, and you're still producing from wind even at night. Then instead of curtailing this power, you can convert it into a green hydrogen production plant and produce hydrogen and store hydrogen.
Yeah.
As much as your tank and compression can take.
Yeah.
However, this idea brings additional revenue stream to the renewable energy generator, and not necessarily for the purpose of using this hydrogen to convert it back to power again. Because it's like I say, every time you convert, you lose some of the value. And here you're losing a lot due to the efficiency of the process. So instead of curtailing the energy, you produce hydrogen, you store it, and you sell it directly to the future gas grid. And this is one of the challenges, that today there is no backbone gas grid for the green hydrogen to be transported directly to the end user. But the idea is to produce it, store it, and then transport it and sell it to somebody who will use it as hydrogen again, or to the fueling station once this has become more popular than today and more cost efficient than today. However, let me put this into context. So globally, I took a quick note here. Just let me quickly look at it, so not to confuse the number. Globally, we need today approximately 100 million ton of hydrogen. Okay. To produce this, only fraction of it is produced from renewable. Less than 1% is produced from green hydrogen. So 99.5% is produced from gray hydrogen. This is number one. Now, this 100 million itself, if we just want to decarbonize it and move into green hydrogen, we would need approximately 1,000 gigawatt of electrolyzers
Mm.
and or 1,000 gigawatt equivalent of renewable energy.
Mm.
How much of renewable energy has been historically installed thus far, from the beginning of utilization of renewable energy to today? We have installed around 4,000 gigawatts.
Mm.
So that's a quarter of all green renewable energy that has been produced thus far. So there is still a huge work to do, in my view, in order to produce green hydrogen to decarbonize industries via renewable energy before we start thinking of using the hydrogen as a source of energy production once again. This luxury we don't have today. We don't want to cannibalize all the efforts that we've done thus far in decarbonizing the electrical grid by just converting it to hydrogen and then converting hydrogen back to power. There are a lot of losses in this process. The most beneficial use is to decarbonize the hydrogen production process itself by electrifying it and connecting it to renewable energy. Of course, you can produce even hydrogen from electrolyzers by connecting it to the grid and pull energy from fossil fuel source combustion combined cycle generators, the CCTs. But this is not smart. Today, you look into where this molecule can contribute to decarbonize, and then push this kind of application before thinking of applications. If I can store it for the energy, if I can generate energy from it, if I can replace batteries and save the lithium that I'm using for the batteries, etc. These are all good applications if we have excess, but we are nowhere of reaching there. Hydrogen itself is, and green hydrogen is foreseen to be decarbonizing or contributing by 10% reduction of the global CO2 emissions by 2050. And this 10% is really big. Okay? So to clear the mind, today, the major application and the major connection between hydrogen and electricity is the production of the green hydrogen via electrolysis process.
What about remote or off-grid energy systems? We touched upon that, but what's the potential in terms of, do you see hydrogen also driving or pushing more for, microgrids and, distributed generation kind of grid? Or how do you see it? Or how do you see the potential for it in the remote and off-grid installations?
I think it's a very good opportunity to scale up the green hydrogen production and allow us to produce green hydrogen in locations where land is cheaper and sun is available. So let us go back to the main issue of scaling up green hydrogen, which is cost. Now, the main cost drivers, as we already know, electricity, and number two is land. So if you are able, and we are, to build the green hydrogen plant in a remote location that is not necessarily connected to the grid, then number one, this allows us to get a cheaper land rather than building it in industrial complexes or nearby the cities, etc. Number one, it allows us to look for locations where more renewable energy resources are available. And the cheapest renewable source of energy today is solar. It's much cheaper than wind. It's even these days even more competitive than the fossil fuel generation for electricity. So building green hydrogen in areas like in remote areas like in the desert, where we have a lot of sun, where the land is cheap, is could be a very attractive solution. This would allow us to capitalize on both cheap land and cheaper source of electricity. Now, of course, there are challenges related to that. And the number one challenge is that, as we mentioned earlier, that once you want to build an off-grid location, then you need to invest in additional equipment to synchronize your grid.
Majd, what future advancements could make hydrogen more cost effective?
We will be looking into multiple, let's say, scenarios that could bring a major breakthrough. Now, electricity price is probably not something that will be dramatically changing over the coming few years. However, the major breakthrough that researchers and engineers are working on continuously is improving the electrolyzer technology. The major losses that happens in the process happens in the electrolyzer, which is the main component of the green hydrogen production. And there are multiple companies who are investing in new technologies that improves the efficiency of the process through implementing changes for the membrane and the material that is separating the anode and the cathode. We have multiple technologies. We have an alkaline electrolyzers, which uses an alkaline as the process facilitator. And we have the proton exchange membrane, or we call it PEM technology. PEM is more modular. We don't produce much larger scale of electrolyzer, so it's still a bit smaller. So today the attempt is to scale it up and could bring additional efficiency enhancement. The most recent technology that we start to see is the solid oxide technology, which is a solid state membrane separating the anode and the cathode, and then the water passes in between. This technology is very promising. It produces a lot of heat still, and scaling it up is a little bit of a challenge. However, it looks very promising, and it could result to much higher efficiency in the green hydrogen production. Now, this is on the technological side. Enhancement on the power electronics could be also there. As you know, we've been using thus far either thyristor-based or IGBT-based rectifiers. There are 1 or 2% losses that comes from the combination of the rectifier and the transformer. And we're working on multiple technologies to enhance this and to enhance these losses, increasing the efficiency and bringing it at least to 1%. And here, every 1 or 2% can count. Now, taking advantage of the economy of scale can also reduce the price heavily. So as we see that the plant scale is becoming larger, then this means we're able to produce all components at big quantities, and this typically results reduction in the capex investment and the capital cost that are required for building the plant. Now, finally, I've heard someone saying that we need to find the fair pricing for the carbon emissions that we are producing today in order to really have a fair comparison between green hydrogen and gray hydrogen, for example. So gray hydrogen is cheaper, but it is producing a lot of carbon emission to Earth. And this is resulting fires, this is resulting floods in some areas, drought in other areas. And the cost of these carbon emissions is high, even though we don't quantify it because it's happening somewhere else. So to bring a fair comparison, regulators need to bring a fair pricing for the carbon emissions that eventually will not result cheaper green hydrogen. However, it will result more expensive gray hydrogen, or a real price for the gray hydrogen that we will be producing. So 3 advancement, economy of scale, technological advancement on the efficiency and the technology of the process, and third, fair pricing for the carbon emissions.
And do you think, like, what about transportation and storage of hydrogen?
Look, this is not so much my area of expertise. However, through multiple discussions with green hydrogen producers and investors, I came to understand something about this topic. So, first of all, hydrogen is very difficult to be compressed. It requires very low temperature in order to compress it, and this consumes a lot of energy in order to cool it and then compress it. So for short distances, this is still okay. However, if we are producing in one location, like in Morocco, Saudi Arabia, and we want to transport the green hydrogen into Europe, for example, then there are more convenient way and safer ways to do so, like converting it into ammonia and shipping it as a green ammonia, and then break the ammonia, which is NH3, down into nitrogen and hydrogen. Nitrogen is also a harmless molecule to the environment. So transportation is definitely a challenge. There are no very detailed regulations. Hydrogen to be transported, safety regulations need to be taken into place because it's explosive. If it is, let's say, if it leaked to air, it could lead to explosion. And there are also technologies in high pressure vessels that are that the transportation companies are investing in. And there are multiple projects in bringing a gas pipeline to make a transportation infrastructure within Europe, for example. There are multiple future projects connecting Denmark with Germany and connecting Spain with France and Morocco with Spain, etc. However, this requires huge investments from the governments, mainly, to build the infrastructure for green hydrogen transportation. This will contribute a lot to reducing the cost. This is correct. We didn't mention that because it's a completely different, sometimes, ecosystem. Once you build this infrastructure, then the cost of transporting hydrogen is becomes much cheaper. You don't need vessels. And producers can just produce and inject into the infrastructure. So it becomes like similar to oil and gas, similar to electricity. You produce and then you inject into the green hydrogen grid. However, there is almost nothing built this far. And there is a pilot project now in the port of Rotterdam in the Netherlands in this regard. So this could, again, contribute, but huge investments will need to be made into building a pipeline for transporting the green hydrogen via pipes.
And where do you see, like, the biggest, let's say, projects at the moment? You mentioned the NEOM project. That's as big as it gets, I'm sure, globally. Is there any similar projects or similar advancements going on globally? And who's leading in that? Who are the countries that are leading?
Yeah. What I used to tell our management is that you need to look where you can get either cheap electricity or an industrial need to decarbonize. So I'll give you some examples. Europe sets clear targets for the carbon emissions for each type of industries. And in order to meet these targets, you need to start today, despite the cost, building your green hydrogen production to connect it to your process. So we see large-scale plants in Sweden because Sweden is very famous for their steel production. And in order to decarbonize steel production, then you need to convert into green hydrogen, because hydrogen is the fuel that is used in the furnaces in order to heat the steel and the iron. So in Sweden, we have seen the largest projects beyond the project in Saudi Arabia at the scale of 800 megawatts. And then by a company called Stegra, and another company, LKAB, is a famous also steel producer. They are investing in multiple phases of 500 megawatt of green hydrogen plant. And then there is the petrochemical industry and the refinery, where companies like Shell and British Petroleum, for example, is investing into converting small portion of the hydrogen they are using into green hydrogen. Some people call it greenwashing. It's not necessarily that. At least they are decarbonizing part of their process. And there they are building, for trials, they build 100 to 200 megawatt plant. So this is relatively large in today's world. So number one driver, the industry, and you saw some examples like in refineries, petrochemical, and in steel. Number two driver is if you have a cheap electricity. We've seen a couple of large projects in Spain and Portugal at advanced stages of the scale of 500 megawatt. These projects are funded by the European Hydrogen Bank. So they provide subsidies for producing green hydrogen. So these are two examples. And regulatory is very important in order to support and facilitate and motivate green hydrogen production. So you saw how emission allowance, for example, EA, they call it, pushes industries to decarbonize and to convert into green hydrogen. And then there are clear regulations in the EU, for example. It's to define what is green hydrogen. It's not something that you just put a plug on a hydro plant that you've been using for the last 100 years, and then it becomes green. It's basically they wanted to build new renewable energy plant to connect it to your green hydrogen plant. This regulation is called RFMBO regulations. And there is another one called CBAM regulation. So RFMBO stands for Renewable Fuel of Non-Biological Origin.
Okay.
And then the CBAM, the Cross-Border Adjustment Mechanism, which means you as an industrial producer, you're not allowed to take your production out of this region in order to decarbonize to say that you have decarbonized. So if you're producing steel, or you're using steel as a main input for your process, you cannot procure it from Latin America and say, look, I'm not making any emissions anymore in Europe. Basically, they will still calculate whatever you're using, then calculate it as a part of your emission allowance.
And finally, where do you see the future opportunities in hydrogen for engineers in general?
I would say today we are in green hydrogen. It's a market that is at its infancy. So we are barely starting, and there will be a need for engineers, expertise in multiple areas, starting with the process, so electrolysis process and the hydrogen production technologies, the hydrogen storage and transportation solutions, the power electronics enhancement, and this is a very important contributor
Mm.
because in the conversion from AC to DC, there are a lot of harmonics that are being produced, and engineers' expertise is very important to estimate what distortions will be exported to the grid and how to compensate it via power quality equipment like statcoms and capacitor banks.
Mhm.
Um, Safety protocols and risk management, and then also general integration between the renewable energy and the electrolysis process. Why this is very important also because renewable energy is a variable by its nature, while electrolyzers as a DC component doesn't like this
Mm.
intermittency. It doesn't appreciate it. It harms its life cycle. So integrating and stabilizing the grid is a very important factor, and technologies and engineers' expertise in this domain will be highly required in order to scale up these plants and connect large-scale renewables to large-scale electrolyzers.
Yeah. Very interesting. Thank you so much for all the information. You've given us a lot of good stuff to think about and consider and contemplate and also research further. I really enjoyed this. I hope you did as well. So thank you so much again for your time. And to all the listeners and viewers of this podcast, if you have any questions, please feel free to leave them um, wherever it is on this platform, whether it's on YouTube or LinkedIn. Feel free to connect with Majd, and I'll also be putting Majd's LinkedIn profile link in the description, and in addition to mine. And as always, if you have any questions, feel free to reach out. And thank you so much for watching and for listening. And I hope you enjoyed it. Thank you.
Yeah, thank you.
Great, Majd. Thank you so much. Yeah, do you want to say a couple of words?
Thank you for having me. What I want to say is basically we're all learning in this field and we're just starting. So don't be afraid of asking questions. Um, the environment is a collaborative environment between engineers, researchers, business developers, investors. Everybody is trying to understand what is the potential and how we can work all together in order to bring green hydrogen into, I'd say it's already real, but into a real market scale production and a real market scale product. We're not there yet today. We're all learning, and there are multiple pioneers that we look forward to work with and learn from.
Well, thank you so much again. I'm excited to now follow the hydrogen journey and see where that takes us. Thank you much.